Good afternoon, all. Welcome to the discussion session of Plates and Cells course offered by NPTEL. The course instructor of this course is Professor Sudhir Talukdar, and I am teaching assistant of this course. Myself, Asif Raza, I am a PhD scholar from Department of Civil Engineering, ISC Bangalore. So today is our first discussion session. What we'll do in this discussion session is that we'll solve some exercises or some questions which will help you in doing the assignments, and if after the due date of the assignments are over, then I'll solve the questions of those assignments. Also, I'll solve your doubts pertaining to lectures, if any. Before starting the session, I'll just ask you guys to uh, use you try to utilize the discussion forum as much as possible. Try to post your doubts, whatever you feel, even if it is small doubt, just post it so that I may resolve your doubts. If I am not able to resolve your doubts in that discussion forum, I'll try to resolve those doubts in the upcoming live session. So please do utilize the discussion forum as much as possible. Yesterday I was not able to record it, that's why today I'm just redoing the work which I did yesterday. So let's start. Today we'll be discussing assignment 0. So let's start. What is the first question? The first question is the ratio of shear stress to shear strain in elastic material is. The first option is bulk modulus, second option is shear modulus, third option is modulus of rigidity, and the fourth option is Young's modulus of elasticity. So what would be the correct answer? So the correct answer of this question is B and C, shear modulus and modulus of rigidity. But we need to know what is A and D as well. So bulk modulus is the ratio of volumetric stress upon volumetric strain, and it is denoted by K. And what is Young's modulus of elasticity? Young's modulus of elasticity is the ratio of longitudinal stress upon longitudinal strain. It is generally denoted by E, while the shear modulus and modulus of rigidity is generally denoted by G. Now let's solve the second question. The second question was what is the solution of an initial value problem given by dy by dx is equal to kx square with the condition that x equal to 1, y equal to 0. So we are given with dy by dx is equal to kx square. So dy equal to kx square dx, integrating on both sides, will get y equal to k x cube by 3 plus c, where c is the constant of integration. Take it, equation number 1. Now we are given with at x equal to 1, y is equal to 0. Substitute above values in equation 1. We get 0 equal to k by 3 plus c, which will give me the value of c as k by 3. Now substitute the value of c. In equation 1, we get y is equal to kx cube by 3 minus k by 3, which can be simplified to get y equal to k by 3 x cube minus 1, which is my solution. So on comparing these two, it gave the option C is the correct answer. Now let's solve question number 3. So question number 3 is a beam of length L simply supported at the ends carried two equal point loads P at L by 3 from either of the supports. If the cross section of the beam is rectangular with dimension B and A, the maximum bending stress in the beam is given by. So let's draw what is given. We are given with a simply supported structure with length L and two equal loads P at a distance of L by 3. And the cross section of the beam is B by A. We need to find the maximum bending stress in the beam. So let's draw first what would be the unknowns in this case. Reactions would be coming out to be this. Take R1, R2 and H1. Summation of Fx equal to 0 will give me H1 equal to 0. Summation of Fy equal to 0 would give me R1 plus R2 is equal to 2P, and summation at moment about, take the point as A and B, so we'll take this equal to 0 will give me what, so R2 into L minus plus P into 12 by 3 plus P into L by 3 equal to 0, which will give me R2 as equal to A to P is equal to P. Substitute this in this equation, we'll get R1 as equal to P. The system will come out to be as R1 as P, P, P and P. So what will be its bending moment diagram? Bending moment diagram would be P, this is my region of L by 3, this is also L by 3, this is also L by 3, and the value would be PL by 3. This is my bending moment diagram. So the maximum bending moment is in this region. Now we have to find the maximum bending stress. We are given with the cross section as B by A, right? Yeah. The moment of inertia for this section is BAQ by 12, right? That is width times depth cube upon 12. Now we know this formula, that sigma by y is equal to m by I. This will now simplify, we'll get sigma my upon I. To get the maximum bending stress, we can take max, it could be m max, y max upon I. I is constant throughout the section, so that would be same. Now the m max is what? PL by 3. Y max, so what is Y max? So we are given with the neutral section, Y max would be this topmost point. So this is what? A by 2. This is A, this is B, so this is A by 2. And the moment of inertia is BA cubed by 12. Simplifying this, we'll get PL 3 to the 6, PL by 6 upon BA cubed by 12, which on simplifying would give me 2 PL BA square. So this is my maximum bending stress, that is 2 PL upon BA square, and the correct option is A. Now let's solve question number 4. So the question number 4 is the buckling loads P of a column hinge at both ends of uniform flexural rigidity EI and of length L can be found by solving the following equation: sin KL equal to 0, in which the K is given by. So we need to find the value of K. So two things which need to be observed is the column is hinged at both ends. So we'll solve the equation. We know the equation EI d2y upon dx square plus py is equal to 0, which can be simplified as d2y upon dx square plus p upon pi y equal to 0. Take y is equal to e to the power mx. So we will get m square to the power m square e to the power mx plus p to the power pi e to the power mx equal to 0. So this will give me square plus p equal to 0. This is always greater than equal to 0. So this gives me m square plus pi equal to 0, which give m equal to plus minus I root p to the power ei. Now, so the equation would come out to be C y equal to C1 cos root p upon x plus into sin root p upon pi x. As the column is hinged at both ends, we are given with the condition that at x equal to 0, y equal to 0, and at x equal to L, y equal to 0. We'll substitute this in the above equation. Take it as equation number 2. So first condition, substituting the first condition, that at x equal to 0, y equal to 0. So in equation 2 we'll see 0 c1 cos root 0 will give me 1, c2 sin 0 is 0. This gives me c1 equals to 0. This simplifies the equation as c2 sin root p upon ei x. Now using the second condition, that is put x equal to L, y equal to 0 in above equation, we get 0 shift to sine root p upon ei L equal to 0. To get the non-trivial solution, we'll see sine root p upon ei L equal to 0. Comparing with the given equation, which was sin kl equal to 0, it was sin kl equal to 0, we get k is equal to root p upon ei. So the correct option is root p upon ei, option B. Now the question number 5. Question number 5 is, which of the following structures is statically indeterminate? So what are statically indeterminate structures? Statically indeterminate structures are those structures whose unknown reactions cannot be solved using only the equilibrium equations. So let's solve this one by one. So the first option is cantilever beam. Let's do this. The first option is cantilever beam. So what are the unknowns in this? Vertical, horizontal, and one moment are the unknowns in this system. So the degree of statically indeterminacy in this is r minus 3 is equal to 4 minus 3 is equal to 3 minus 3 is equal to 0. So this is a statically indeterminate structure. Now the option B, what is it? So we are given with a propped cantilever with an internal hinge at the center. So in this also we'll have the unknown reactions in this, while an additional reaction in the propped side. So the degree of indeterminacy will be d is equal to r minus 3 plus we have an additional equilibrium equation which will get using this. This will give me that the summation of moment at this point is equal to 0. So we will have an additional equilibrium equation. So 4 minus 3 minus 1 will give me 0. So this is also a statically determinate structure. Now let's see the third. We are given with a 3-hinge parabolic arc. The unknown reactions would be vertical reactions at the support, horizontal reactions at the support. So the degree of indetermination would be r minus 3 minus 1, as we'll have an additional moment equation from the hinge part. So as an overall we'll be having 4 minus 3 minus 1. This would also give me, so this is the 3-hinge parabolic arc is also a statically determinate structure. Now taking the option D, which is 2-span continuous beam. So suppose if we take a case where only vertical loads are applied, suppose. So what will be the unknowns in this? We'll get unknowns as this reactions. The degree of indeterminacy in this case will be r minus 2. That will give me 3 minus 2 is equal to 1. So the degree, so the among these options, the correct option would be the option D, and that is degree having a static indeterminacy as 1. Now let's solve the equation. Question number 6. We are given with a cantilever beam of length L with flexural rigidity EI, which is subjected to a point load P at the free end. The elastic strain energy stored in the beam due to the bending. We have to neglect transfers here. So let's solve it. So we are given with a cantilever beam with length L, point load at the free end, and the flexural rigidity as EI. So at a section X, what do we have the moment at this section? The moment at X is minus Px, right? And the bending moment diagram of this is PL. The question asked is, what is the elastic strain energy stored in the structure? So elastic strain energy stored in the structure is from 0 to L mx square upon 2ei dx. So it will come out to be minus Px square 2ei dx is equal to, take the stuff outside, 0 to L x square dx p square upon 2ei x cube by 3, 0 to L. So this gives me p square L cube by 6 ei. The correct answer would be option 1. So this solves the assignment 0. Now I'll just solve like what were the typos which were in the first week of the lectures. So let me go through that as well. So first typo was in the equation 1b and 1c in the page 9 of the lecture. So here in the equation 1b, the tau yx would be there in the place of tau xy, and in equation 1c it will be tau zy instead of tau yz. But in the long term, in the long run, using the moment equilibrium, these both are one and the same, so numerically it won't give an error, so it's correct. Now come to the this part, equation 21. So in the equation 21, let's solve this. So equation 21, what do we have? We have 1 upon r and t as cos alpha del upon del x plus sin alpha del upon del y minus sin alpha dou w by dou x plus cos alpha dou w by dou y. Let's solve this. So this will give me dou by dou x of rho w by dou x plus cos alpha plus sin alpha dou by y of minus rho w dou x plus cos alpha dou w by dou y. Simplifying this will get minus cos alpha sin alpha dou square w by dou x square plus cos square alpha dou square w dou x dou y minus sin square alpha dou square w dou y dou x plus sin alpha cos alpha x square w by dou y square. So substitute trigonometric identities as cos alpha sin alpha equal to sin 2 alpha by 2, cos square alpha minus sin square alpha as cos 2 alpha, and minus del square w by dou square is equal to 1 upon rx minus dou square w upon dou y square as 1 upon ry dou square w by dou x dou y is equal to del square dou y dou x is equal to 1 upon rxy. So substituting this in the above equation will get 1 upon r and t as 1 upon rx sin 2 alpha by 2 plus cos 2 alpha 1 upon rxy minus 1 upon ry sin 2 alpha by 2. So simplifying this will get 1 upon rx minus 1 upon ry as sin 2 alpha by 2 plus cos 2 alpha times 1 upon rxy. This gives me 1 upon r and t. So correct this in the equation number 21. This would be 1 upon, the first term would be 1 upon ry minus 1 upon rx. Now the most common, or like most people are having doubt in this, or like how to take the gradient. So let me solve this, like how to take this gradient part. So let's solve this. We were given with an element. So I have given with an element a, b, c, d with the length as dx along this x direction, and along the y we have the length dy. So this element ABCD displaces and goes to the point A dash, B dash, C dash and D dash. So from A to A dash, the displacement along the x direction is u, while displacement of A to A dash in the y direction it's v. So when we want to find what would be the displaced value of b to b dash in the x and the y, similarly for c and d. So let's solve it step by step. So we want to find displacement of, okay, let's see, displacement of B in the direction of x would be displacement of A in the direction of x plus the change in the displacement when we reach to the point B from A. So what is this change we're talking? See, first part is displacement of A in the direction of x, which is u. So the displacing so the point A is displaced to A dash in the direction of x as u. The net change would be del u by del x times the distance between these points A to B is dx. So if dx is 0, if dx is not there, that means A B coincides with A and dx would come out to be 0. So the displacement of B would be the same as displacement of A, which will come out to be u. So this justifies. So as a result, the displacement of B to B dash in the direction of x would be u plus dou u by dou x times dx, right? Similarly, for the point C in the direction of y would be in the direction of y would be displacement of A to A dash in the direction of y, which would be v, plus the change of this displacement as we move along the y direction, and the total distance between point A to C is dy. So this gives me the displacement of the point C to C dash in the direction of y. Now the displacement of B to B dash in the direction of y, what will it be? Displacement of B in the direction of y would be the displacement of A in the direction of y plus the change in the displacement value, change in the displacement when we reach from A to point A to B. So what is this change? So the displacement of A in the direction of y is v plus this change dou v by, and this is the change is what we move along the x direction. As we move from A to B, the change is along x direction, so we take dou v by dou x times dx, right? So this would give me the displacement of B to B dash, that is v plus dou v by dou x times dx. If you follow the same logic, we'll get the displacement of C to C dash as u plus dou u by, what will be, we move along the y direction in this case, and this will be u plus dou u by dou y dy. Now suppose if you want to find the displacement of D to D dash in the direction of x and y, what will it be? So we now have the displacement value of B and C and A. So either we can find the displacement value of D from B to D or from C to D. So let's first proceed from B to D and see what do we get. So displacement of D in the direction of x would be displacement of B in the direction of x plus the change when we move from point B to D. So the displacement value of D in the direction of x, displacement of B in the direction of x is u plus dou u by dou x dx. This is displacement of B in the direction of x. The change when we move from, so we have to take the change of the same value dou u by dou x dx, and this is like we move from point B to D. This is along the y direction, so the change is with respect to y, and we from B to D, the distance value is dy. So as a result, the displacement of D in the direction of x is come out to be dou x dx plus dou u by dou y dy plus dou square u dou y dou x dx dy, right? A further assumption can be done, like if dx and dy are very small, then dx times dy would be much lesser than 1, which can be neglected as neglected. So the final result can be turned as dou u plus dou u by dou x dx and dou y dy. Your second order is neglected, but let's let it remain here in this case. Now the same value, like displacement of D in the direction of y would be displacement of B in the direction of y plus the change when we move from point B to D. The displacement of B in the direction of y is v plus dou v by dou x, v plus dou v by dou x dx, correct? So the change would be v plus dou v by dou x dx times dy. The result will give me as dx dou v by dou y dy dou square v dou y dou x dx dy. So the final results come out to be as along the x direction. Let me write it this in different color. So this come out to be u plus dou u by dou x dx dou u by dou y dy plus dou square u dou y dou x dx dy. Similarly from D to D dash, it is v plus dou v by dou x dx dou v by dou y dy plus dou square v dou y dou x dx dy. This we solved when we move from B to D. What if we solve this, get the displacement of D when we move from C to D? Let's verify it whether the value is coming out to be same or not. So we want to find the displacement of t in the direction of x. This we get when we move from b to d. This is also from b to d. Now we are trying to select from c to d. We get the same value or not. So the displacement of c in the direction of x plus change when we move from c to d. So displacement of c in the direction of x is u plus dou u by dou y dy. U plus dou u by dou y dy plus it will be, as we move along the x we reach from c to d, so the net change would be dou u by dou y dy dx, and it will come out to be dy plus dou u by dou x dx plus dou x dx dy. So these are for the displacement of d in the direction of y, displacement of c in the direction of y plus change and reach point c to d. So this will be v plus dou v by dou y dy plus dou by dou x v plus dou y dy dx. This gives me v plus dou v by dou y dy dou v by dou x dx dou square v dou x dy dx dy. So when we compare 3 5 6, so when comparing 3 and 5, what do we see? U dou u by dou, yeah, so they are one and the same. Similarly 4 and 6, dou v by dou y dou v by dou x, they are one and the same, so it's correct. So this is what I wanted to show. Okay, what next? Yes, question lecture 2. Okay, so many people were asking like, what is u naught? U naught is the displacement of the middle surface by the action of in-plane load. So normally when we take the case of bending, when the in-plane load action is not taken into account, so the points on the neutral surface remain as it is, they do not displace. But when the in-plane load is taken into account, it might be possible that the points in the neutral plane like this might get displaced to point a somewhere point, which can be taken as u naught. Now the points in the upper or lower points above the neutral axis or lower axis would also be displaced, as well as they will be rotated at the slope. So the net displacement would be u plus z times alpha, like this. So u naught is what? U naught, just you need to say like, is the displacement of middle surface by the action of in-plane load. This does not affect much the equation, only just the shear strain values has an additional term, dou u naught by dou x, dou v naught by dou y, and the shear strain will have this additional term. But in Kirchhoff theory, we neglect the middle surface stretching, and ultimately it reduces to this equations. Equation numbers 14, 15, and 16. Okay. So one typo which need to be corrected is page number 10 of module 1 lecture 2. In the equation of mx, in this first line in the second equation, here it will be plus instead of minus, because sigma x is equal to e minus 1 e upon 1 minus nu square times epsilon x plus nu times epsilon y. This epsilon x has minus z times dou square w by dou x square, which is there in the later equations. It should not be there in the previous equation, so please correct this one. Similarly, for my, the first equation on the right hand side, it will be plus instead of minus, so please correct this. mxy is correct, these are also correct. Okay, what next? There are a few more typos, I'll just let you know. Okay. So wherever it's written theta or seems like theta, you need to write it as nu. I think these values are corrected in the live lectures, but in the PDF notes of these lectures, in the correction is still not made, so please correct these typos. This would be new. Similarly, further we'll find this kind of typos. Yeah, so yeah, equation number 24, 25, 27, 28, 29 and 30, please correct this. These are new. Here also new. Please follow these corrections. In equation 39 and 40 as well. So I think, yeah, these many were corrections need to follow. So that's it for today. Okay, so at last I would ask you people to just post your doubts, whatever doubts you have, just post it in the discussion forum, so that in the upcoming lectures, if there is a need, I would discuss those things if needed. Okay, see you on next Saturday, that is on 6th of August, 3 p.m. Okay, bye.